readings. Let's say we have a plane in 3D, which we can have an example, for example, x plus 2y plus 3z, and this is one way to denote it. And this means that any time we have a 3D, we have a 3D plane described by this equation, and any point on this plane, if we know two parameters, for example, we know we want to be on that plane for x equals 1, if this is x-axis, this is y-axis, this is z, for y at, here is y, at 2, then we put it in this equation, so that would be 1 plus 2 times 2 plus 3z equals 1. If we have two parameters known, we can count the third one. So we have 5 plus 3z equals 1, 3z equals minus 4, z equals minus 4 over 3. So we had x and y known, and we wanted to know what's the third parameter that's located on that plane according to this equation that describes every point on the plane. This is one way of describing planes. And another way is that we have a parametric form, and that plane will be described by a point, which will be a 3D point, of course. We're dealing with 3 dimensions, so 3 parameters, x, y, and z, plus parameter. Now, by parameter, I mean something different. This is an arbitrary scalar that can multiply that vector, plus 2 arbitrary scalars multiplying 2 different vectors that lie in the plane but are not parallel to each other, so they're not equivalent in direction. So we have a point A that definitely lies on the plane, so you have to think of that one. Then we have a point, then we have one vector and another vector that are both in the plane. So if we have the plane, we have the plane somewhere, well, there's some vector, let's say this one we will call something, and another vector. They are both in the plane. They don't go perpendicular to the plane or somehow at an angle to the plane. They're really lying in the plane, okay? So there's 3D space and these two vectors. Then we also have something perpendicular to the plane and therefore perpendicular to both these vectors. That's a normal vector that will go perpendicular to the plane. And that vector, by the way, we can get from this equation, and we'll use it. So our goal is to convert this expression into this expression, and the only thing we need is to know an example point on the plane and two vectors that lie in the plane. And how to get that? Well, as follows. First thing to note is if we have a plane, there is a perpendicular vector denoted n, the normal vector, that's perpendicular to the plane. The parameters of which, the x, y, z coordinates of which, we can get from the coefficients of this base equation, this general equation. Therefore, it will be 1, 2, 3. So the normal vector to the plane that's described by this equation is 1, 2, 3. 1 in x direction, 2 in y direction, 3 in z direction. And now, we know for parametric form, we need two vectors that lie in the plane, which will mean they lie in the plane. They are perpendicular both to this n, to this normal vector. So all we need is to think of those. And perpendicular vectors have a dot product of 0. So let's take this 1, 2, 3, and we want to dot product it with some vector with 3 entries, the dot product of which with 1, 2, 3 will be 0. Dot product is calculated by the way, in case you don't know, this times this plus this times this plus this times this. So let's think of what will work. I can think of values as long as they're all, not all 0. Example could be, I say first one is 1. Again, we think of two numbers and the third one we calculate out of it. So we need the dot product to be 0. 1 times 1 plus, let's say 1 times 2, so 1, 1, and minus 1 works. Because 1 times 1 plus 1 times 2 minus 1 times 3 is 0. That works. So our first vector that lies in the plane, because it's perpendicular to the normal vector, is 1, 1, minus 1. That works. And that can, for example, go here or here, doesn't matter. T and S are both just arbitrary multipliers of scalar multipliers for the vectors. Because what matters is that non-zero, that the length is non-zero, but what matters is then also mainly the direction of the vector. and that these two vectors are not parallel to each other, so that they give more than the information about the line. They give that information for that plane. They both lie in the plane, but they're not parallel to each other. So one vector of those two can be this one, and another, let's think the same way. Again, we need a dot product with 1, 2, 3 to be 0. So let's take other numbers. Let's take 2 and 3. So 2, 3 and minus 2. 2 times 1 plus 2 times 3. No, that's wrong. Actually, we could also we can do even easier. We can do 0 and something, perhaps. We can actually do 0 and let's say, for example, 3. So 0 times 1 plus 3 times 2 minus 2 times 3. That works. That again is dot product of 0, if we think about it. So our second vector we need is 0, 3, minus 2. An example, alright? It can be anything as long as it's a non-zero vector, because 0 would give no information. That would be redundant. That whole term would reduce to 0 and would go away from this equation, so we don't want that. But as long, and also let's always make sure these two are not scalar multiples of each other, which they cannot be there if there's a 0 and here's not a 0. But often it could happen if one's using numbers quite randomly, one can end up with two vectors that are scalar multiples of each other. But so be careful about that. But it didn't happen here, that's good. And therefore they're useful and they fulfill the function we want them to have. So we only get this equation, but now we managed to get two vectors that we can plug in here and have the parametric form. And as I said, it doesn't matter if we put this one here, or this one here, and this one here, or this one here. I mean, either will go in either place. Of course, we don't repeat one of them twice. We put both there. So 1, 1, minus 1 here, for example, and 0, 3, minus 2 here. And T and S, as I said, are just real numbers. But yeah, they can be 0 actually also. So they're real numbers. And one last thing that's actually easier than one might think is to get the A. So we need a point that's on the plane. I'll keep it there until we get that point. So all we need for that is to know any point on the plane. And any point is easy to get. We can always use that basic idea from the beginning, plug in two values and get the third value, as we did before. I mean, I can put 1 and 2 and get that fraction for Z. Or I can plug in 0 and 0, for example. I could do that. That's probably quite fast to do. So if x and y are 0, these are x and y coordinates, 0, 0, then the equation becomes 3z equals 1, so z is 1/3. So I got a, and then I can put it here. So 0, 0, 1/3. So now we got it. Now we have the parametric form of the same plane. So the same plane that was described by this equation is now described by this parametric one. And this method is quite easy to do, because if we want to just reproduce the same idea again, or the same process, it's really fast to do. The harder thing about it perhaps is the theory, because we need to remember that there's always a normal vector to the plane that's described by the coefficients of these three terms. And of course, if the equation is organized differently and it's not first x, y, z, it's switched around, you must pay attention to it. And the entries are always x, y, z. So follow the coefficients for those entries. Alright, so x is multiplied by 1, 2 is multiplying y, 3 is multiplying z. Therefore, the normal vector is that 1, 2, 3, the one we used. The one perpendicular to the plane, and therefore those vectors, any vectors that lie in the plane, must be perpendicular to the vector 1, 2, 3. And with that idea, I'm just now repeating what we did. We thought of any free entry vector that's non-zero, because that wouldn't give any additional information. We thought of two different vectors that are not just scalar multiples of each other, but they have a different direction. But they'll, of course, both by this rule be inside the plane as long as we follow the dot product to be 0 with the normal one. We thought of two vectors that fulfill this. We put them there. and now we span the whole plane. Think about it. We take a point that's in the plane, let's say perhaps this is A. And then we have two vectors. Let's call this U, let's say this is U and this is V. So these two are U and V. And if we start with A, then anywhere that U and V move the location to with their directions will stay on the plane, and also because they're not parallel to each other and they're not non-zero, one can span any point on the plane with them. And so we can put any real numbers for T and S and get some point on the plane, and that proves that it is equivalent to exactly what the plane was stated to be by the initial equation.